Welcome learners. In today's lecture we are going to conclude the fourth chapter and we are going to talk about how can we find the energy stored inside an electrostatic field. So basically the idea is that what happens when we move different charges, let's say sum of charges or discrete set of charges inside the vicinity of a source charge, and we say that the work is done by all these charges. So how can we define the energy expended in doing the work done? So the idea is that how can we find the energy inside an electrostatic system? We already have talked about potential, and we know that the potential is extracted from the work done. That is, the equation of the work done was Q E dot dl, and we know that potential was work done in moving a charge, which gave us the value of E dot dl. And if we talk about it, then it's an integral value of initial to final value. But now we want to know that how much is the energy expended in finding out this potential, or basically what is the energy flow, or how can we trace this potential energy from the work done among the charges. So this is the idea of today's topic, and let us see what we know so far and how can we find the energy in terms of the work done. So we know that the energy density. So let us start by first understanding what is an energy density, or how the energy is stored inside the field. So this is our starting point. So we say that if we have an electric field, let's say over here represented by E, and we select any small area inside this electric field, so let us call this rho v. So we say that the energy density is defined as the total amount of energy stored in per unit volume is known as energy density. So it means that if we have a region such as this and we want to see how much is the energy confined in a small area, we can define it as energy density, which is basically the total amount of energy inside this area per unit volume. So this defines the energy density, and then we are going to use this concept and relate it to the energy storage inside the field. So the energy density and energy storage will be vice versa used. Now in order to find this energy, we say that this is the potential energy. So in order to find this potential energy, we must first find how much is work done by the external force on the charges inside the field. So in the field, so we say that we discuss two scenarios for this. In the first scenario, we say that, so this is our first scenario. We say that we have a charge Q and it has created its own field. Now we take another charge, let's say a test charge Q of t, which is lying at infinity and where we know that the potential is 0 volt, and we bring it inside the field of the first charge. Let us call this Q1. So this test charge can be placed in close vicinity to Q1 at point A, it can be placed at point B, it can be placed at point B. So this charge or test charge can be brought to point A, it can be brought to point B, or it can be brought to point C, but it is coming from the reference of infinity. Now when this happens, there is an external force that is doing this work done, and work done is done by bringing this test charge from infinity to any point, let's say point A. Now the energy or the external source has to maintain its energy such that the test charge is halted at point A, and thus it doesn't move. So the idea is that the external source has to hold its energy. So we can say external source holds its energy such that the test charge remains at, let's say, point A inside the field of charge Q1. This kind of hold or this kind of energy is known as the potential energy. So thus we start our discussion for energy storage with the context of the potential energy. If somehow the external source lets go of this energy, what might happen is that this test charge, which is Qt, may not remain at point P or point A in this scenario, and it may leave the field, it may wander somewhere else. So this test charge may wander somewhere else when the external source lets go of its potential energy, and in that case we say that test charge has now taken a kinetic energy because it is now starting to move. So this is one scenario that we have been discussing a lot, and this has helped us in providing us the equation for the potential difference and potential at any point. Now let us take another scenario where we want to find the energy for distributed charges. So now in the second scenario, we say we have a system of charges and we want to see what is the potential energy in this case in terms of the work done. So basically we want to find WE. So before going into the mathematics, let us say what is this scenario about. Now we consider that we have an empty universe. So let us say I'm drawing it a flat empty universe. This is my empty universe. Okay. Now I bring a charge from infinity, or let's say in this universe, the first charge that appears is Q1. So this is Q1. It is over here plus Q1. Now, since this charge is becoming present from infinity, let's say this is my reference point at infinity, to Q1, it is going to experience no work done because there exists no field in the beginning. So the charge 1 is going to create its own field or region of field. Now we bring another charge, let me call this as Q2, and this is at infinity. So this is at Q2. Then we have another charge Q3. Then we have another charge Q4, and it can be many charges like Qn. So now there are system of charges that are lying in reference plane infinity. So now I bring second charge Q2 from reference inside the field of the first charge Q1 at any point, let's say A. Similarly, I can bring the next charge into the vicinity of Q1 at point B, and the third charge can also come, let's say, to point C. Now in this scenario where the charges are coming from infinity like Q1, Q2, Q3 and Q4, they will experience a potential in the form of a work done because now they have to move against the field of Q1. So in this scenario, there is going to exist an energy expanded, or there is going to be a potential that is going to exist, and we say that a work done is possible for these set of distributed charges. Now let us mathematically prove what is the work done for the second scenario. So in order to see the mathematics of this, we say that we have a distributed set of charges. So let me write it as distributed set of charges which were at infinity. So reference is infinity, and now we want to find what is the work done by these charges. So we say that the work done, so let me use this space. So work done in moving charge 1 initially in the empty universe was 0 because it was not faced with any existing field. So then what is the work done in moving the second charge, Q2. Now again, initially Q1 didn't do any work because the universe was empty. There was no field that was opposing its motion or movement. But the second charge, when it was brought close to this first charge Q1, it experienced an energy expansion potential, or it got some work done against this field created by Q1. This means that Q2 experienced some work done which represented as a certain potential V, and we define its subscripts of potential as V21. So where V21 is basically location and the effect coming from a source. So this is what the subscript at the potential is going to mean. So charge 2 basically experienced a potential at point 2 coming from source Q1. So this is what the statement means. Similarly, if I say what is the work done in bringing the third charge Q3 and work done in bringing the fourth charge, and we can go on, but let us stick to fourth charges. So this means that Q3 will experience the same potential at 3, but now coming from source 1, which is Q1, plus it is going to experience a potential again at point 3, but this is now coming from the second source Q2. And if we go for the fourth one, so Q4 will experience a potential at point 4 coming from source 1, Q4 will experience a potential at point 4 coming from source 2, and Q4 will experience a potential at point 4 coming from source 3. So this is how we have taken, and if we have more than charges, so it will keep on going like this. So this is the behavior of the work done inside this empty universe. So this means that we can summarize this into a single value, that the total amount of work done in the form of the energy expended, WE, is going to be the sum of all of these charges from Q1 to Q4, but it can go to Qn. We are restricting it to the 4 charges. Is going to be Q2 V21 plus Q3 V31 plus Q3 V32 plus Q4 V41 plus Q4 V42 plus Q4 V43, and it can go on as well. So this is what we are getting. Okay, now let me call this as equation 1. So in order to move forward, I want to rewrite my equation 1. So how can I rephrase it or restate it? So restating equation 1 on the basis of this criteria. If I say I have a charge Q3 that is experiencing effect from 1, it means that if I have another charge Q1 location at 1, it will experience the same from source 3. To put it in simple words, let's say if this is Q3 and the potential it is experiencing from source 1 is written as Q1 divided by 4 pi epsilon R13. It is the same as saying that if I have Q1, the potential experienced by Q3 or point charge is Q3 divided by 4 pi epsilon R31. So this kind of relationship is basically called mutual work effect or mutual energy effect, that if we have two charges, as per Coulomb's law, they are going to experience the same attraction or repulsion if we take it with a reference charge, or if the relationship between two is considered, they will experience the same attraction and repulsion among each other. So this means that equation 1 can be restated as, so I can write equation 1 as, let me change the color for this, I can write equation 1 as WE is equal to, so I'm going to change the subscripts, Q1 V12, this is what I can write, plus Q1 V13 plus Q2 V23 plus Q1 V14 plus Q2 V24 plus Q3 V34 and so on. So what we have done is we have replaced this in this form. We have replaced the second one or the first element. So this Q1 is replaced as this one, Q3 is replaced as this one, this third element is replaced as such, the fourth element is replaced as this, the fifth element is replaced, and the sixth element Q43 has been replaced as V34. So this is now my equation number 2, which is a restated version of the first equation. So now what I can do is I can add both the equations and then we can continue from there. So let's add equation 1 and equation 2. So this means my equation will be 2We, and now I can write it as such. So if it is charge Q1, I can take the voltages as common, V12 plus V13 plus V14, and it can go on for the rest. Then I have plus Q2, then I have V21 plus V23 plus V24, and it can go on for the rest. If we have n charges, plus Q3 is equal to V31 plus V32 plus V34, and it can go on, and let me call this as equation number 3. So this is the result of adding equation 1 and 2. Now if you look at equation 3, the potentials are giving us a new information that if we look at the first set of potentials, and the same will be applied to the second set and the third set. So in the first set of potentials, we see that V12 means that the potential at location 1 coming from effect of 2, potential of V1 coming effect of 3, potential at V1 location coming from the effect of 4 is basically all are located at a single location of V1. Same goes for V2 and same goes for V3. This means that equation 3 can be written as, so I can say that V12, V13, V14, they have a same location, which is V1. Similarly, V21, V23 and V24, they have the same location as V2, and so on and so forth. So this means that my equation 3 can be written as, so what is equation 3? 2We and sum of charges. So I can write it as We, I'll take 2 on the other side at the denominator, and it is going to be Q1 multiplied with all the locations at location of potential 1 plus Q2 multiplied with location at potential 2 plus Q3 multiplied at location of 3, and it can go on for n vectors. This means that the final equation for the work done in the form of energy of discrete system of charges is represented as 1 by 2. You have the summation of Qm with Vm, where m is from 1 to n, and this is the equation, let me call this equation 4, that is giving me the potential energy stored inside the system of charges, which means that I can also find the potential energy stored if I have continuous charge distribution, because the summation can be represented as an integral, let's say, of volume charge. Q will be replaced by its volume charge density, which is rho v dv, and it will be followed by the potential V of n. So this is the expression 5, which is again representing the potential energy for stored, or this is the stored potential energy for continuous charge distribution. Hence we have figured out that the scalar element, which is the work done over here, is represented as stored potential energy for the discrete system of charges or continuous system of charges. So now let us talk about how we can further represent this stored energy in the context of electric fields. Till now we have seen that the energy is stored when we are talking about the charges. So one charge is interacting with the other, if it's a system of charges, or it is basically a continuous. But what happens if I want to find this stored energy? So I want to again see that this stored energy affect in the form of fields. So let us see what other way we can represent this. So we know that the stored amount of energy by charges is given as 1 by 2 for continuous charge distribution volume rho v dv multiplied with the potential. So can I figure out how much is energy stored in the form of fields now? What it means is that previously we talked about the energy stored in terms of the relation of charges, whether they were discrete charges or they were system of charges continuous. Now I want to see that what happens if the energy is represented or the stored energy is figured out if the fields are being generated from these charges. So what is going to be the effect in terms of the E field or the D field? Can I have an expression for that? Yes, we can. So from our base equation which we saw previously, which defines the continuous energy stored, I can rewrite it as the stored energy can be represented as 1 by 2. Since this is a volume charge distribution, I can represent rho v in terms of the Maxwell's first equation, which means I can write rho v as divergence of d, then you have voltage v of m, and then you have dv. So I just replaced rho v with divergence of d over here, which is the Maxwell's first equation. Now we can use an identity to solve this divergence of d part, where the identity is such. So the identity we can use, the vector identity we can use. So let me use this portion. Vector identity is such. If I have divergence of voltage with electric flux, it approximately equals to voltage multiplied with divergence of d plus d multiplied with divergence of v. So this is the vector identity that we can use. Since we want to replace this portion with Vm, so I can focus on this equation and extract the remaining part. So this means that voltage divergence of D can be written as divergence voltage of D minus D divergence of V. So this is what I am using. So my equation then comes out to be that work done is equal to 1 by 2, and I can write it as volume, and now the value comes out to be divergence V of D and minus D multiplied with divergence of V, and this is dV. So now this is the new equation which I have taken, which is this portion over here. So once I have this, I can then continue further analyzing this. Now if I look at this portion of the equation, I can use the divergence theorem. So I can now apply the divergence theorem on the above. So what is the divergence theorem? So divergence theorem, if you remember, was that if I have a closed surface integral of electric flux in a area or small, it is equal to the volume of divergence of d into dv. This is the divergence theorem. So what I can do is I can apply divergence theorem onto the equation above, which means I can write the WE as 1 by 2. Since this is the volume portion, I can replace it with the surface distribution, where I know that this is d and the del operator is as such. So I can write as 1 by 2 surface integral V of d multiplied with d of s. So I have basically replaced this portion with this part, where d is this portion over here. So this is Vd of d of s, and the remaining equation remains the same, where it is 1 by 2 volume d multiplied with divergence of v dv. So this is what I am getting. Now if I look at the first part of this equation, this automatically comes out to be 0 because the integral and the integrand are reaching towards infinity. What does this mean, or how this part becomes equal to 0? We'll go to that, but first let us write the remaining equation, which is negative 1 by 2 volume integral d dot divergence of v dv. So now how this portion comes out to be 0? This comes out to be 0 because we know that the equation for potential relies on a distance of 1 by r. Electric flux density's equation is dependent on the distance of 1 by r square. So if I take the dot product of v of d, it comes out to be 1 by r cube, and since r tends to infinity, it will be 0. So that's why we have taken the first term to be 0. And the second point is that we are integrating based on the volume, not the surface. So it automatically goes to 0. But this is the technical reason behind it. So now we are left with electric flux over here, and then we have the gradient or divergence of V. So now since this portion is known to us, we know that we can replace it with what? 1 by 2 volume integral. We have the electric flux density d, and this portion is what? It is minus V. What is minus E? This minus E is basically the electric field intensity which we can find from the gradient. So the E over here is basically, if you remember, minus gradient of the potential. So we have replaced this with E. This means our equation becomes 1 by 2 integral volume d dot E, and this is d of E. So this is the equation we are getting for the energy, where we can see that the energy stored can be represented in the form of field lines, where the field lines are electric flux density d and the electric intensity V. We can further simplify it as well if you want, that it can be represented as epsilon E square dV. So this is the second variation of the square, where E is now acting as a scalar element, as we have used the value of d is equal to epsilon E to get this part of the equation. So now we have two equations for stored energy in the form of electric and electric flux field lines. So this is the representation that we are getting. Okay, now how about if I want to find the energy stored inside a coaxial cable? So now what about if I want to find the energy stored inside a coaxial cable, or a portion of the coaxial cable? So we can just remember the equations for this. We don't need to get into the mathematical proof of it. So let's say if I have a coaxial cable, this is the inner side, this is the outer side. We know that electric field is always existing between the conductors and not on and inside the conductor, and the inner portion is represented as A and the outer radius is represented as B. So we know that the conductors can be represented as set of capacitors, or because they are two conducting sheets. So the energy stored in a capacitor is equal to half q v into A. This is the capacitor's energy. This is energy stored in a capacitor. So if you want to find what is the energy stored in a coaxial cable, we know that the energy stored basically is the product of the charges and the potential at that point. So based on this, what is the charge inside a coaxial cable? So it is 2 pi Al rho of S. This is the total charge of the inner conductor. We have seen this in the previous chapter. And what about the potential of the inner conductor? So it is A rho of S divided by epsilon natural log of B by A. So this is the potential difference between conductors. We have already looked into this equation. So once we have Q and VA, the value of WE, or the energy stored inside a coaxial cable, comes out to be A square rho S square natural log B by A divided by epsilon pi of L. So this is the expression that you should know whenever you want to find the energy stored inside the coaxial cable. Since the proof is not part of this course, that's why we are not going into the proof. And one more thing associated with the energy stored or energy density in terms of the electric field D or E is that we can write it in differential form. So the equation that we have figured out over here, this one, can also be written in a differential element. So this means that if we have energy, and this is another formula that is going to be utilized a lot, so I'm just going to write it. Energy field or density for the charges or the field is given by 1 by 2. You have volume of electric flux density and electric field intensity dV. So this is basically the energy stored in the form of the fields. So we can also write it as the differential amount of energy stored, which is going to be equal to 1 by 2 d dot E divided by dV. So this is the incremental or small amount of energy stored inside the fields with the units of joule per meter cube. So this is information for you to know. So now let us come to a numerical that will conclude this topic and the fourth chapter of this course as well. So the problem says that find the energy stored in free space for the region of r, theta and phi. So this means this is a spherical coordinate system given the potential field V. So let us do one portion of this problem, and the second part is similar, you can try yourself. So we need to find the energy stored in the free space. So this is a spherical coordinate system because we have the value of r, theta and phi. The ranges are given. So the value of potential is V equals to 200 by r, and we know that the energy stored inside the fields, because the charge is radiating, is given by 1 divided by 2 volume integral d dot E dV. So this is the equation which we have, and this another variation of this equation if need be is 1 by 2 is equal to volume epsilon naught E square dV. So these are the equations which can be utilized to find the energy stored inside any field. So since the second part of the equation seems more reasonable for volume integration because we have just electric field to deal with and it's a magnitude value, so we can use this part of the equation. So in order to find electric field, we know that, so this is our base equation, I'll highlight it, which we want to use, and we are focusing on this second part. So we know that electric field can be figured out if we take the negative gradient of potential, and potential is already given to us over here. So what we can do is we can figure out what is the potential or gradient of potential. Since this is a spherical field, so the value will be partial derivative of V along R, A of R plus 1 by R partial derivative along theta A of theta and plus 1 by R sine theta partial derivative of V along phi A of phi. So this is the gradient of V for the spherical coordinate system. So if you look at this equation, we know that the potential is only given in terms of R, so automatically this portion and the theta and phi portion will become 0. So we just need to find the partial derivative along R. So this means we'll write partial derivative along R for the value of 200 divided by R along A of R. So 200 is the coefficient, I can take it out and I'll be left with 1 by R. So it will be partial derivative of 1 by R along A of R. So is the value which we'll get after taking the partial derivative of R. Now this means then our value of electric field comes out to be, so negative and negative becomes 200 divided by R square along A of R. We get the value of volts per meter, but we want to have the value in its a scalar component, so I can represent this E as E of R along A of R, which means I will be having a value of 200 divided by, or it will be 200 divided by r square, since AR and AR dot product will be equal to 1. So this is how we got the value of E. Now let's utilize this equation to get our answer. So the work done comes out to be 1 divided by 2 volume integral epsilon E square d of V, and it comes out to be 1 by 2. Now we have a triple integral. This is r, this is theta, this is phi. The value of epsilon as it is, and E square becomes 200 divided by r square whole power square, and the value of dV, so this is the differential element along rectangular the spherical coordinate system, so its value is r square sine theta dr d theta d phi. So the ranges of the integrals are such: r is from 0.002 meter to 0.003, theta is from 0 to 90 degree, which is pi by 2, and phi is always from 0 to 90 degree in this case. And we have 1 by 2, so I can bring it out as a coefficient. And then we have epsilon naught value, and this is going to be 200 divided by r4, and this is square. So we have r square sine theta dr d theta d phi. We can get rid of r square from 1 square over here, and we can multiply these elements to get the coefficients before doing the integration. So it comes out to be 1.7708 into 10 raised to power minus 12. This is minus 12, and now inside the integral I have theta r phi. This is sine theta dr d theta and d phi. So the limits are for r, theta and phi. So once you have all these values and integration, hopefully now you can do the integration. I'll write the final answer to it: 1.7708 into 10 raised to power minus 12. Inside the integral I get the value of pi by 2 into 1 into 1.66, or sorry, it is pi by 2 into 1 and into 166.67. These are the solutions of the integrals of r, theta and phi, and finally the work done comes out to be 46.35 into 10 raised to power minus 6 joules for the first part of the potential given. I leave the second part for you to solve along the same lines, and that's concluding our lecture series for the chapter 4.